Nuclear energy. Part 1. Nuclear energy is the energy in the nucleus of an atom. Atoms are tiny units that make up all matter in the universe. Energy is what holds the nucleus together. There is a huge amount of power in an atom's dense nucleus. In fact, the power that holds the nucleus together is officially called the strong force. We know that the energy released through chemical reactions is of the order of a few electron volts per atom, whereas energies involved in nuclear processes is million electron volts per atom per nucleon. This means that for the same quantity of matter, nuclear sources will give a million times larger energy than conventional sources. 1 kilogram of coal on burning gives 10 raised to power 7 joules of energy, whereas 1 kg of uranium, which undergoes fission, will generate on fission 10 raised to power 14 joules of energy. Fission. In nuclear fission, atoms are split to release the energy. As neutron is a neutral particle, so it does not experience any Coulomb's repulsive force when bombarded on the nucleus. Therefore, neutron is considered as an ideal projectile for induced nuclear reactions. Enrico Fermi found that when neutrons bombarded various elements, new radioactive elements are produced. However, when a neutron was bombarded on a uranium target, the uranium nucleus broke into two nearly equal fragments, releasing great amount of energy. 0N1 plus 92U235 give 92U236 gives 56Ba144 plus 36Kr89 plus 30N1. A lot of heat and 3 neutrons per fission are released. These 3 neutrons cause nuclear fission in 3 more uranium nuclei. Fission does not always produce barium and krypton. A different pair can be produced. For example, 0N1 plus 92U235 give 92U236 gives 51Sp133 plus 41Nb99 plus 40N1. The energy released, the Q value, in the fission reaction of nuclei like uranium is of the order of 200 MeV per fissioning nucleus. The source of energy in nuclear reactors which produce electricity is nuclear fission. Nuclear reactor. A machine which has a controlled and sustainable nuclear reaction for any of the following several purposes: to produce power, to supply neutrons, to induce nuclear reactions, to prepare radioisotope, or to breed fissionable material is called nuclear reactor. When 92U235 undergoes a fission after bombarded by a neutron, it also releases extra neutrons. These extra neutrons are then available for initiating fission of other 92U235 nuclei. Nuclear chain reactions are series of nuclear fissions, splitting of atomic nuclei, each initiated by a neutron produced in a preceding fission. In fact, on an average, 2.5 neutrons per fission of uranium nucleus are released. The fact that more neutrons are produced in fission than are consumed raises the possibility of a chain reaction. It was found that neutrons released in fission of a uranium nucleus were so energetic that they would rather escape than to initiate another fission reaction. The slow neutrons have a much higher probability of causing fission in 92U235 than fast neutrons. Moderator. The function of moderator is to slow down the neutrons produced during the fission process. As the neutrons produced during the fission process are very fast and are not suitable for producing fission in the reactor fuel. Water, heavy water, D2O, and graphite are commonly used moderators. Multiplication factor. It is a measure of the growth rate of the neutrons in the reactor. For K is equal to 1, the operation of the reactor is said to be critical. If K becomes greater than 1, the reaction rate and the reactor power increases exponentially. Unless the factor K is brought down very close to unity, the reactor will become supercritical and can even explode. The reaction rate is controlled through control rods made out of neutron-absorbing material such as cadmium or boron.